All right, and so now we are turning our focus into studying the derivatives of exponential functions. So here we are looking at exponential functions. All right, so quickly as a brief reminder, the following functions are exponential functions. So 2 to the x. If we have y equals 2 to the x, it's an exponential function. If we have f of x equals 3 to the x, it's an exponential function. So quickly as a brief review right here, then an exponential function has a base being a positive number. So these big numbers right here, they are being the base, referred as the bases of the exponential functions. And the input arguments of our functions are being found in the exponential components of our functions right here. And so 2 to the x, the input goes into the power, the exponents. And so the same here, 3 to the x, the input variable goes into the exponent. And that's how these functions are being referred to as exponential function. And so being an exponential function, really it's a family of many functions of the same similarity here. They have one positive base and being raised to an input variable. And so really any constants, we can be looking at a constant being a fraction, and we, as long as the number is being positive, and we can raise that to an input, an exponential input right here. And there we have for ourselves a just fine looking exponential function. Or even nasty looking number, basically what I mean is irrational number, like a pi right here. It's a positive number, doesn't have to be nice looking. But now we can raise that to the x power, we have another exponential function. And so usually when you arrive at the first year calculus, which is about this class, or somewhere in the pre-calculus class, then a college pre-calculus class, and you are getting to know what the constant e right here. So e itself is roughly 2.718 and a lot longer. And so in some other lecture, I am going to be delivering the how a historical development of how this value e came about. But so just now, e here is a constant, simply a constant among, just like any other real values out there. It's a positive value, and it's also an irrational number. So pi we have learned since first grade, second grade. Ever since we learned about finding areas or circumference of a circle, we learned about pi being 3.14 since a long time ago. But now it takes us into pre-calculus to actually get to know what the other known constant out there, the e constant, 2.718. But now in the end, being a constant and a positive value, we can go ahead and we can create an exponential function. And so e to the x is another exponential function among the entire family of all exponential functions out there. Okay, and so now I am going to turn our main focus into finding the derivative of this function. And so let's start our study here with this given function, f of x equals e to the x. Okay, so shockingly, such a weird looking number. It's not rational. It's a very irrational number, and the only thing being, the only thing making it an exponential function is simply because the base is a positive value. And so it's not nice looking like a 2, like a 3, or a 1000. It's an e. But surprisingly, we will be studying, and this function will be among the most popular functions in the family of exponential functions out there. And so now let's go ahead and learn how to find the derivative of this function. One thing to keep in mind, when we are attempting to find the derivative f prime of x, we are not going to bring the power down. Power rules is not applicable to this family of function, because you see there is the difference between e to the x, or maybe I shouldn't bring up e to the x, 2 to the x, and x squared here. In this case, this is a power function. X squared is a power function, an input variable x value being raised to a power 2. Whereas here we have a base 2 being raised to an exponent. And that's why this function here is not a power function. This function here is referred as an exponential function. And here is a power function. So power rule works on this one. We can use a power rule for power function. But power rule will not work for exponential function. And so if anyone mistakenly find the derivative of e to the x in this way, bring the power down, x times e to the x minus 1. So I have to say sorry that this is not the way to get our derivative of e to the x. And the derivative of e to the x is nowhere near to this kind of answer right here. All right. And so, as a matter of fact, we are in an entirely brand new family of functions where we haven't found any specific methods to find the derivative for e to the x. So now we have to go back to zero ground right here. And what I mean zero ground is we have to go back to and stick with the limit definition of finding the derivative. And so now to start out finding f prime as a general derivative for e to the x. So now this is what I need to do. We need to set up the limit definition. Go back to that limit definition where we're creating that general difference quotient, f of x plus h minus f of x, and divide the difference there by h. And we're taking the limits, treat the problem here as a limits problem where we're letting h approach 0. All right. And so in that way, and so I keep calling this limit definition as the zero ground or ground zero, simply because in case that we've never learned any technique that directly find this derivative, we always have this tool right here as the tool for us to discover new function. So who knows, 10 years from now, 20 years from now, any viewers who view this video would become a mathematician and on your way to recognize the derivative of a completely brand new function that no one in this day knew its existence yet. Then trust me, you will have to stay with this formula. Okay? And so limits as h go to 0 of this general difference quotient. But so f of x is e to the x. And so in that way, in the next step, my difference quotient becomes so x plus h. So remind yourself again, the anatomy, the structure of an exponential function is that the inputs will go into the exponents part of your function. So in that way, here's my f of x plus h going to be written as e to the x plus h, because I substitute x plus h for x in my function. And now minus f of x, which is simply e to the x, repeat it itself again. And now after creating that difference here, I am now going to divide by h. And then of course, this problem will be a limit problem. But right now we're just holding on to that limit problem. Okay? And so, again, I have to emphasize that at this point, limit laws are simply not going to work yet. Won't be applicable here, because if we simply use limit law and treat things like plugging in the h equals 0 value in the expression here, we are going to run into e to the x minus e to the x over 0. So it's an e to the x minus e to the x is a 0. So 0 over 0 is another inconclusive answer. One day in some future lecture, you will understand what this form has and what the exact formal name for a form like this when you're taking limits. But for now, allow me to use the term inconclusive. We don't have an answer for a situation like this. But that means we have to advance further into the algebra of this difference quotient. So in my next step, well, algebraically, this is what we already knew. e to the x plus h, the power of the rule of exponents allowed us to bring that first term in as a product of e to the x times e to the h. Okay, and again, feel free to pause the video or even stop the video and search over the web to convince yourself about this. What I'm trying to say is that for any base right here being raised to a power n plus m, it always equals to a to the n times a to the m. And so in that way, that is how I bring my e to the x plus h term into e to the x times e to the h. And now the other term in my numerator stays the same, minus e to the x. And we are dividing by h. And this problem is still, in the end, a limits problem where we're letting h approach 0. Okay? And so at this point, again, limit laws will fail to work at this step because we're still going to run into that 0 over 0 setup right there. So it's still an inconclusive situation, but at least we develop things a little further. So then let's use the algebra further. I am going to use my algebra, and at least now among the two terms I can recognize a common factor. So there's a common factor e to the x here. So I am now going to factor e to the x. And now what I'm looking at here is e to the h minus 1. And we're dividing by h. And we're taking limits as h go to 0. Okay? And so in that way, at this point, you have seen this reasoning of mine in some of the earlier lecture, and here I'm making that reasoning again. The entire limits problem here is based on, or is aiming at, the h variable being the main variable, because here in this limits problem, h is the variable of our concerns because it's going to 0. X here even though being a variable as well, but has nothing to do with the limits because we are not letting x go to 0. So in other words, if we're aiming at h being the main variable in this entire problem, then e to the x can be regarded as a constant, or just simply be regarded as a coefficient of this entire expression, simply because the h is the one that is driving the limits value. And so in that way, limit laws here, the reason I mentioned this now is because limit laws now allowed us to, once we recognize we have a constant coefficient, then we can bring the constant coefficient in front of the limit, and simply just the limits problem turned into just the limits of this expression here, e to the h minus 1 over h. So now we just produce for ourselves an e to the x, which is completely independent with the h variable, and then multiply that e to the x with the limits problem e to the h minus 1. All right. And so at this point, you can pause the video, or you can stop and look back at some earlier lecture. But does this limit here look familiar to anyone viewing this video of mine right here? At least if you've been following my video lectures since the beginning days that I delivered video lectures in calculus, you must recall something about this. And if you do, go ahead and pause the video, or even stop the video here, go back to my earlier video lecture to recall for yourself what this limit's value will be. Okay? And so at this point, after you have seen or have quickly reviewed for yourself, this limit I have shown earlier, this limits turn out to be 1. And so in the end, our overall limits problem here, the e to the x as a constant coefficient, it stays there, e to the x. Multiply with the entire limits problem here, we have done that. And this was among the special limits that I went over in some of the earlier lecture, times 1. And so we don't have to write times 1. So in the end, our answer is e to the x. So what have we done, and what were we doing? And now what have we got? Okay, and so let's make a formal statement here. So in my next board, as a formal conclusion. So what we have found now is that if our function is f of x equals e to the x, then what have we found? Taking the derivative of e to the x is simply itself e to the x. What a special function. The function itself at start, f of x equal e to the x. And now taking the derivative f prime of x also equals e to the x. And so now, congratulations, now you have discovered the derivative of that special function e to the x. When you take the derivative of e to the x, it's e to the x. And so a couple other ways of, couple other forms of this rule over here. When you have an e to the x, take the derivative. Okay, so we have seen this alternative symbol, take the prime of that. It's an operator indicating that we're taking the derivative, assuming the variable of this expression here is the x, as being currently indicated here. And so that derivative there is e to the x. That's another way, in short, to remind yourself that derivative of the e to the x function is e to the x. Okay? Or you can think of this dx symbol that I've introduced quite a few times. Taking the derivative of e to the x gives you e to the x. That's another way of writing that statement like that. But so now in the end, we have found that the derivative of e to the x is e to the x. Okay? And so now in this way I'm going. So it looks like we found something. We made some discovery right here. But then what about the other exponential function? Because e to the x we're looking at here is not the only exponential function out there. Is not the only exponential function existing out there. We have 2 to the x is an exponential function. We have 3 to the x. We have 5 to the x. We have 1/2 to the x. We have what else? Pi to the x. Like I mentioned earlier, anytime we have a positive constant value, we can always raise that to an exponential power, and there we create for ourselves an exponential function. Okay? And so now let me bring up, so I'm gonna go through how about 2 to the x, but I hope viewers are going to start recognizing some generality as I go along over here. Okay? So let's look again. So what about we are now given f of x to be 2 to the x, and we want to find the derivative, we want to find out f prime. Okay? And as we have seen that before, then we have to go back to the zero ground again, because even though we found the derivative for e to the x, okay, but that's just one rule specifically meant or intended for the e to the x function. And so, you know, what guarantees? Nothing guarantees that 2 to the x, that as I suggested here, will work the same way. And so we have to go back to zero ground, meaning let's stay back with that. Let's go back and stick with that limit definition again to really find the derivative of this function. And so now, again, I'm setting up my difference quotient, f of x plus h. And there will be some similarity with the steps as how we were doing that when it was e to the x earlier. We take the limits here, f of x plus h minus f of x over h, and we're dividing that quotient here, that difference by h, and then we take the limits of this quotient as h go to 0. Okay, but now since we switched from e to the x to 2 to the x in our f of x function right here, then the problem will become 2 to the x plus h minus 2 to the x over h. And yes, that is a limit problem. And then being a limit problem right here, again, I need to remind anyone viewing my video, limit laws are not applicable at this point yet. The limit laws fail here because we're going to end up with a 0 over 0, which is an inconclusive answer. So, and that means we have to carry on with the step, move on further until we can do some algebra work and simplify our expression so that we can come down to some actual limits. Okay, and so in that way, the same trick I have done with e to the x plus h earlier, now we can do the same thing again. 2 to the x plus h, 2 to the x plus h can be understood as 2 to the x times 2 to the h. Okay, it's just another algebraic property of the exponential function. And so in my next step, this is what I am going to be doing. That equals, so now I have limits as a limit problem, and here I'm looking at 2 to the x plus h, 2 to the x times 2 to the h. That's what I meant, and minus 2 to the x, and we're dividing that by h. Okay, and so there's still some similarity with what we have done back in that e to the x function. And so now I am going to continue further. And of course, again, limit laws still fail at this point, meaning it's still going to give us a 0 over 0, an inconclusive answer. That means we have to continue further into getting our actual work. So continuing further, this is what I'm ending up. I am going to factor out the common factor 2 to the x this time. So now I'm looking at factoring out 2 to the x, and then what remains in parentheses, what's left in parentheses is 2 to the h, the difference 2 to the h minus 1 over h, and we're taking limits as h goes to 0. All right, and then again, the very same reasoning, the very same explanation I've made earlier when it was e to the x. Now this 2 to the x here, even though we have a variable x, but it's completely independent with h as the variable, simply because our limit problem is concerning about h approaching 0 instead of x going to 0. And so in that way, 2 to the x, my point is 2 to the x now can be regarded as a constant coefficient again. And being a constant coefficient to this entire expression, we can feel free to bring that in front, and the real limits problem now only turns out to be the limits problem of 2 to the h minus 1 over h. And whichever value of this limits problem, we are going to multiply with 2 to the x in front. Okay? Because that's where we already apply a little bit of limit laws into our work, even though it didn't get us anywhere too far yet. And so now, again, but we have to be clear this time that unlike the e to the x, unlike e to the h minus 1 over h, taking limits as h go to 0, that limit there was going to limit to 1. But this limit of ours right here, it's not really 1. Okay, and right now if we simply applying the limit laws here, the limit laws will fail being applied here again. And so let's go back to table approach, because if we apply the limit laws, it's going to give us 0 over 0, and there hasn't been any special technique to handle this limit. So let's go back to the table approach. So this time I am going to show everybody a little bit of how we can use and how useful decimals that I've been using the whole time can be. So with my favorite graphing device, surprisingly, it is also a pretty good calculating tool for me. So this is what I'm doing. So this time I am going to disregard my graphing window here. So I am going to just drag this command area to extend that bigger, and we don't even have to sign in or anything like that. Even without having an account, Decimal is still allowing you to have free fun with all these graphings and a lot more than that. So now I am going to insert a table. Okay, and here I'm going to adjust. For beginners, I recommend that let's adjust the variable here. So here's the x column and here's the y column, but here let's adjust the x column to be the h column, because our main, once again I remind anyone that our main expression here, our expression that we're considering limits is working with the h variable, and that's the reason why I'm I'm using the h as my independent variable column. And now for this y column right here, now I'm going to type in the function. And we don't need to type equal sign or anything like that. So now in parentheses 2 to the h, okay, minus 1, all right, and then divided by h. So there's my setup for 2 to the h minus 1 over h. It's a difference quotient. And now my attempt here is we are trying, so from the right hand side, I can start with 1, and then we have output value for 1. And then I'm going to hit enter. Now I'm going to go closer to 0. So how about 0.1? Closer to 0. I have a value being 0.71773 and a lot longer. And that still didn't get us anywhere yet. Let's go further. How about negative? How about 0.01? Okay. And that gets us down to 0.695555, something like that. Okay, and even further, even closer to 0, but still from the right hand side. So it looks like right now I'm working on the right hand side table approach for getting this limit of 2 to the h minus 1 all over h. And now I'm looking at 0.001. Okay, and here's my value for that. And what about another value? How about 0.001? 0.0001. Okay, 3 zeros before the 1 right here, and now it's 0.6931. Okay, and I'm going to go a few more entries. So 0.00001. Okay, and so with technology, it can help us to do the limit problem with table a lot faster. All right, and now how about 0.00001? Okay, 5 zeros before a 1. So now it looks like the limit value here gets slower and gets lower and keeps staying around 0.693, something like that, 0.693 for about 4 entries already. So now let's keep going a few more entries further. So this time I'm going to go with 60 and then a 1 right here, very close to 0. Okay, and we got this. And so it looks like we're right about 0.6931472. Okay, and even how about just one more, I promise. 0.5670 and a 1. Okay, and now so we're down to 0.6931471.8. So instead of 2 at the end here, we're looking at 1.8. Okay, so that's the right hand side table. So it looks like there's a value existing, definitely not 1, definitely not 1. Okay, and so, but of course, because these values are quite irrational, so I'm not making any viewers to guess any value, anything like that, but at least it does look like in about 6 decimals, and it stays about the same with 0.693147 for at least a few entries already. So now let's look over, and I'm holding on to the actual limits here, because I know that there's going to be some limits, but it's just a little hard for us to expect what that limit is. What about the left hand side table? So the same table here, I can just start picking values from the left hand side of 0. Recall for yourself, from this expression, we're letting h go to 0. Okay, and so now I'm going to start out with negative 1, and we're looking at a 0.5 for this difference quotient. And now I'm going to change to negative 0.1. Okay, and I get positive, and so far the output values are all positive. So now on my left hand side table, is starting out right here, and then so the second entry is negative 0.1. Should I put those 0 there to make it a little more clear? Okay, and then now how about negative 0.01? Okay, and we're looking at 0.69 again. So it's starting to seem like it agrees with the limits on the other right hand side right here. Okay, and now I'm going to continue further. Negative 0.001. Okay, and we got 0.692. So it's 0.66 earlier, but 0.69 for 2 entries. 0.69. Okay, let's go further. Negative 0.0001. Okay, so 0.69 again, but this time 0.693. Okay, and then negative 0.0000. 1. Okay, 4 zeros and a 1. So 0.69314478. And a few more entries. Okay, so now I'm going to start picking up speeding up the process a little bit. All right, and then all right, so I keep getting closer and closer to 0, pretty close to 0. All right, so now that's about pretty good enough, and these entries now look really close to each other. From the left hand side we came to 0.6931417. Right hand side came down to 0.693141718. So, and they're all positive value. Okay, so now I am going to show everyone another one, and still we're on decimal screens right now. Let me now enter a new cell. So left hand side table as you have seen and right hand side table as you have seen all came to a value kind of like this, and it's, for now I admit it's hard to tell the actual value because it's the two answers here are pretty irrational. So now it's not really out of nowhere. I am the instructor here, so I knew these values, but then I want my student to experience and experiment this. So how about anyone arriving at calculus know the natural log function? So natural log of, how about try natural log of 2? Okay, so natural log of 2 decimal is powerful enough to give me a decimal calculation of natural log of 2, and let's observe the value. So 0.693, ooh, does that look familiar? 147, 0.693147, and then the 18056. Okay, so it looks like our limits here. So now we come to a conclusion. All right, so it looks like this limits here turns out. So I did that completely based on a numerical argument, a numerical approach table. But so now we're looking at this limits turn into a natural log of 2. Natural log of 2. And so, and 2 to the x remains the same as a coefficient, multiplying it. So now bingo, we found for ourselves our final derivative of this. This is 2 to the x. Multiply with natural log of 2. So, but natural log of 2 is just a value, it's just a constant coefficient. And so now, what is our final derivative for 2 to the x as a function? All right, so if our function start being 2 to the x, it's an exponential function, then okay, if f of x equals 2 to the x, then the derivative f prime of x is, you see, what's easy to remember is that it looks like at this point right here, two exponential functions we have covered already, and they are having this similarity. At least in the derivative, the derivatives always repeat the actual function itself at some point. So here, when it was e to the x, the derivative was the exact repeat of e to the x. But now when it's 2 to the x, at least we had that 2 to the x being repeated here. And what to remember is natural log of 2. Okay? And so I am going to, so here's a rule, but sadly this rule is only, being specific for 2 to the x function. Or we can formulate this, and I don't want to put it in a box or anything like that. But 2 to the x, right? Take the derivative, that gives me 2 to the x times natural log of 2. Okay, all right. And so now let's go back to my other board. And now I can even speed up the process a little more, and some later part of the problem, I am going to have my viewers to get some answer on your own right there. So what about this time? Let's push our attention to, turn our attention to the function f of x equals, how about 5 to the x, okay? How about 5 to the x? It's another, so like the e to the x, like the 2 to the x. Here we're looking at base 5 positive value, so 5 to the x. Let's find the derivative. So the derivative again, and you can start doing your independent work with me as you are viewing my video here. But so f prime of x, we never had any special rule for to handle a general, because we haven't found one. We haven't found the way to find derivative for any general exponential function yet. And so for each one of these, we have to stay with the zero ground right there, the one that we have to stick with the limit definition. And so f of x plus h again minus f of x, such a powerful little starting point for any derivative problem over h. And we take the limit as h go to 0. And so yes, hopefully that any viewer following along with my video here is doing work independently on your own. Don't just wait for me to get to that step right there. Okay? Go ahead and get your own step, be ahead of me, and when I get there, you compare with your answer. So now that f of x plus h, in this case here, in our case, we're looking at 5 to the x. So that means we have, so f of x plus h becomes 5 to the x plus h. And I'm subtracting 5 to the x. Okay? And then I'm dividing by h, and we're taking limit as h go to 0. All right, and then so again, it has all that similarity with the earlier two problems I have done. And so let's speed up the process a little bit. Now I can see this as a 5 times x. See, 5 times x times 5. I mean 5 to the x times 5 to the h. So that means my first term here becomes 5 to the x times 5 to the h minus 5 to the x again, okay, and all over h, and the problem remains as a limit problem. And still, neither one of these steps right here is possible to apply the limit law. So we're going to have to keep advancing until we can bring it down to a form where limit laws will apply. So now, again, similar work we have done earlier. I can factor out the 5 to the x, and what remains inside of my parentheses now is 5 to the h minus 1, okay, and over h, and take h, go to 0. So, and I once again, one further step, I argue the same way again. This 5 to the x is completely independent with this limit problem in terms of h. That means now I can pull that in front as a coefficient for now, and then whatever the limits of this expression, 5 to the h minus 1 over h right here, okay, get to 0. So now go ahead and start putting up some experiments right here. Go ahead and try using the table approach, just like how I was doing that, okay, just like how I was doing that earlier with the 2 to the h minus 1 over h right here, and find out for yourself what this limit turned out into. So, and feel free to pause my video and even rewind that to an earlier point to see how I was doing that with decimal, and I hope you also caught a little bit of instruction of how I operate with decimals right there to get the answer. All right, so now at this point, hopefully you've had some thoughts in mind, but yes, I agree with you. So 5 to the x remains there, but this overall limits, after hopefully you already tried the right hand side table, getting to some nasty looking decimals, and the left hand side table, and then it's getting to some nasty decimal answer again. But it should look like the two left and right hand side tables agree to some ugly looking decimals. And so now the truth here, that limit of yours, this limit right here goes to natural log of 5. All right. And so that was the part where I want all of my viewers to be able to try independently using decimals. And it's completely started out on scratch here by using the table approach. Okay. But now it's time to point out a good generality. So let me get to my other board. So now we found. So the one we just now found, and I still have 2 to the x still here. So if our function now is, if f of x equals 5 to the x, okay, then our derivative turns in turn out to be f prime of x equals 5 to the x. See, we're repeating like the e to the x, we're repeating the function itself. We're repeating 2 to the x here, we're repeating 5 to the x here, and back in the e to the x function, we repeated e to the x. And so 5 to the x times times natural log of 5. Okay, or as a short form, taking the derivative of that 5 to the x function is going to give us 5 to the x times the natural log of 5. Okay, so now it's time to start recognizing a generality, because viewers of mine, I believe, have seen enough. So what I see here is that in my final derivative of 2 to the x, of course it has the 2 to the x repeated, but then it has natural log of 2. How do you think that 2 here is related to our beginning function? Looks like it's that base, and everything I'm saying it's to trigger your observation sense. But see, this 2 looks like being the same with that 2 in the base of our 2 to the x function. Okay, and then so let's look over to our 5 to the x function. So the function was 5 to the x. Here's our final derivative, 5 to the x being repeated. So it looks like it already had that similar components. It repeats the exponential function itself. And then natural log, it uses its natural log as well. Okay, and then this 5 here, it looks like it's the same way how I recognized the 2 here earlier. So it looks like, again, that 5 here is agreeing with the base 5 back in our original 5 to the x function. So now in that way. So how about before I really get into the actual generality of all a to the x function, let's look at e to the x again. If you already had something in mind, then let's think about that. If we apply this generality, I have not written it out yet, okay? But think about it. Our derivative here, couldn't this derivative be e to the x? It has that repeated part right there, okay? But now multiply according to what we kind of found, even though we have not confirmed and formalized it yet. But multiply with natural log of e. The e here is agreeing with that e, the original base of our function. And natural log of e, natural log is a log base e of e. You've learned from algebra that natural log of e is 1. And that's why our function earlier, our formula earlier, the derivative of e to the x equals e to the x, is not contradicting with what we have found here. So now at this point, 3 times in a row we ran into some similarity really good. We recognize a pattern pretty clearly in 3 separate problems. So now it's time to bring everything into an actual formulation. All right. So now it looks like generally sort of like an extended version of exponential function. If our function started out being just any a to the x, doesn't have to be e to the x, even though it could. Okay, f of x equals a to the x, and of course the base a here has to be a positive base. Okay, so now then in that case, formally speaking, f prime of x. Okay, pause the video. I believe you already had in mind what I'm about to write here. So pause the video, write it down for yourself first, and when I get there, I hope you agree with me. All right, so f prime here is actually a to the x repeated times natural log of a. And yes, that's our formula for finding any general, the derivative for any general exponential function. So in the short form, a to the x, the derivative of any a to the x, any base a, as long as a is a positive base, then it's a to the x times natural log of a. Okay, that's another way of writing the formula. Okay, or we have another symbol right here, an alternative, a different symbols, the Leibniz symbols, d dx. We're taking the derivative of a to the x function. Okay, and that turns out to be a to the x times the natural log of a. Okay, 3 different ways how we are expressing our rules for derivatives of exponential functions. And so now back in my first board here, then I am going to put all the rules we have learned here together. So earlier in our lecture, in the beginning of our lecture here, then we looked at derivative of e to the x, and that gave us, taking the derivative of e to the x is simply just e to the x itself, okay? Or alternatively, using this d dx symbol, taking the derivative of e to the x is e to the x. Yes, we found one specific rule, very special rule, specifically intended or meant for that e to the x function. And then as an extension of this, the entire family of exponential function being a lot broader than just being a lot more than just e to the x, then we're looking at generally for any a to the x, taking the derivative gives us a to the x times natural log of a, okay? Or in a different way of writing, taking derivative d dx of an a to the x function, that arrives at the final derivative a to the x times natural log of a.